Okay, so I just added a trait module with a forward function. I don't think you can actually make it callable like I don't think you do. I don't think you can set forward like that, but it doesn't matter. Like that's not even that important. But so I made a struct neuron that takes a weight vector and a bias, and I was thinking it could store its own activation, but I guess you don't do that. So it's just a weight and a bias, and then a new function which takes a use size. Oh, I think I did this yesterday on stream. I don't remember. Anyways, you initialize it with a random uniform distribution, both the weight and the bias. That's pretty easy. Then I implemented a trait module, and then I implemented module for neuron. I think that's kind of premature, but whatever. Okay, and then we implement the forward pass. So the forward pass is I fold, this dot product initialized with B, which is the bias, and then I apply the tan H. And here, here's the exp. So the exp is the tan H. I forgot. Because there should be plus minus 1 plus 1. Yeah, okay. And then here's the subtract. Oh, wait. I don't know. Honestly, I should have written a bunch of tests, but it doesn't matter. So now we're going to do layer. And I think he just... Yeah, okay, alright, so... I'm just gonna keep them, whatever. So first, impl layer. And, and all this is going to be is n in u size, n out u size. And then all we have to do is can't I just do for each? I don't know what the difference between for each and map collect is. Like I feel like, well, let's just see if this works. But I don't know if this is gonna work. But I do closure expected to take one argument. What if I just do map? Oh wait, I know what happened. I think I can just do this. This has to be a blank, and then this has to be an n in. Okay, but then layer. Why isn't that right? And then we want to do impl module for layer. And then here, wait, but this, what? Oh, is it? Okay. Oh, yeah, this is kind of janky, but I probably have to clone it. I don't know. I mean, really, the trait thing is kind of overkill.
Literally, a layer is just a list of neurons. And then how many neurons do we have? We take that as an input argument here. How many neurons do you want in your layer? Number of outputs in this layer. And so we just initialize completely independent neurons with this given dimensionality, and we call on it, we just independently evaluate them. So now instead of a neuron, we can make a layer of neurons. We have two-dimensional neurons, and let's have three of them. And now we see that we have three.
Okay, so let's try that. So layer new. So the inputs is 2 and the outputs is 3. And this should just work as before, right? But then what did he... Oh.
Three independent evaluations of three.
Wait, so what I want to do actually is...
different neurons. Okay, and finally, let's complete this picture and define an entire multimodal perceptron, or MLP. And as we can see here, in an MLP, these layers just feed into each other sequentially. So let's come here, and I'm just going to copy the code here in the interest of time. So an MLP...
I'll just keep it how he has it, I guess. And so what happens here is there's no prepend? What? Is that real? It's probably just dot insert 0. Okay, but I don't actually care about this. So, O of n is actually super stupid, but that's okay. Okay, so we're just going to do, and now it's the insert 0 and n. Then we're going to do n, so this is an index. So what we want to do is we want to do layer new n outs 0, or no, index n out index plus 1, something like that, and then dot collect. Okay, so now we have the so this is the layers. Then we're just going to say MLP layers. Ugh, God. Okay, whatever. I will just do that then. It's a mutable reference to a vector. Alright, fine. So now what we want to do is import module for MLP. Okay, let me figure this out. So, we have inputs, right? So, okay, so let me just do the first layer. So the first layer, we would say self dot layers first dot forward. What? What is first? First return some stupid. Okay, so here's the first thing. Can I do this? Let O1 be a totally untyped thing. Then we just do for. I'll probably have to coerce the slice into vec or whatever, but in any case, we do this. I'll probably have to clone it. I think that's it. Oh. I think I can just clone it. No? Cannot move. Oh, but it's probably still cheap, but it's not like... Oh, first, okay, so there's a lot of problems. So mute, so that solves one problem. What is the error? Okay, now we have the ownership issue. No, it's not the ownership issue. It's... Temporary value dropped while borrowed. Wait, first off, I don't even think we need to do this. Oh, nice. And here, I don't even need this. So now I want to see, how does he do a forward pass? He just makes a bunch of layer sizes.
We're taking the number of inputs as before, but now instead of taking a single pinout, which is the number of neurons in a single layer, we're going to take a list of pinouts, and this list defines the sizes of all the layers that we want in our MLP. We want 3, of course, as an MLP. And there we go. That's it.
Okay, I'll try that. Wait, I started with 2. Alright, well, I'll change it to 3. And then this is just going to be a vec of... And I think... Can I do this? Let me see if I don't do it. If I pass it, it'll probably yell at me, right? But we'll do 441. Okay, and then it'll say needs a expected mutable reference to a vec u size found vec I32. So yeah, so all we have to do is just turn it into a mutable reference. The data's dropped immediately after anyways, but that's it. Okay. So then, instead of n.forward, I want to do mlp.forward and then make this value new 4. And then out should be a single... Whoa, it's a big expression. Yeah, the graph is getting very big. Oh yeah, that doesn't work. Okay. That's pretty cool.
The forward pass of MLP. To make this a little bit nicer, you see how we have just a single element, but it's wrapped in a list, because a layer always returns lists. So for convenience, return outs at 0 if len outs is exactly a single element, else return full list. And this will allow us to just get a single value out at the last layer that only has a single neuron. And finally, we should be able to prod out of NFX. And
I don't like that at all.
Imagine,
I think that's a janky thing, but...
are now getting relatively involved. So this is an entire MLP that we're defining now, all the way until a single output. Okay? And so obviously you would never differentiate on pen and paper these expressions, but with micrograd, we will be able to backpropagate all the way through this and backpropagate into these weights of all these neurons. So let's see how that works. Okay, so let's create ourselves a very simple example data set here. So this data set has 4 examples. And so we have 4 possible inputs into the neural net, and we have 4 desired targets. So we'd like the neural net to assign or output 1.0 when it's fed this example, -1 when it's fed these examples, and 1 when it's fed this example. So it's a very simple binary classifier neural net basically that we would like here. Now let's think what the neural net currently thinks about these 4 examples. We can just get their predictions. Basically we can just call n of x for x and axis, and then we can print.
So I think what I want to do is... Can you even do that? Is that even allowed? What happens if you try to do let x equal vec of 1, 2.5? What happens? It just implicitly... No. Yeah, so it's very restrictive, which is fine. So, okay, I want to make it that take... I don't really know what the best thing is. Okay, I'm down to copy this function. Or actually, no, wait, I should learn this. Okay, this is cool. All right, so wait. Yeah, this is a general. This is nice. All right, so below value. Below add traits. I want to do can't I just do this? You have to put can't I just do this then? Oh, because you need to refer to it. But you don't have to. You don't necessarily have to do where. Where is just because it simplifies things later. This is an impl of into iterator, where the item is something that implements into f64. Yeah, and then it returns a vec of value. And then all we have to do is items dot map item value new item. And I think we might have to call into, but and that's it. Into iter map value item and into collect. All right, so yeah, pretty simple. So now I can go down here, back to main, and I can start to make the data set. So presumably I can make a vec of vex. So where's his data set? Did I go back to
Layer of neurons is just.
Oh, that was weird. Okay. Translate this into rest. Okay. Now we have 3 vex of values, which is good. And what we want to do is let ypred equal x's.map x mlp.forward x. The thing is, it's huge because each of them store the whole thing. So what I want to do is But okay, wait. Let me just make sure that I know what's happening. Because if I do this is not called debug. This errors. So I need to implement this, right? So I think all I have to do is where is traits? I think all I have to do is impl display for a value. Do I need to give it a type, function, format result? I don't know how to do this. Oh, because what the hell am I doing? Wait, what just happened? Is debug the exact same? So then I need to get rid of that it derives debug, right? Oh yeah, but now I just have to change this to this. No, here we go. Okay, cool. Nice. Alright, so we got the forward pass and we changed the printing.
So these are the outputs of the neural net on those four examples. So the first one is 0.91, but we like it to be 1. So we should push this one higher. This one we want it to be higher. This one says 0.88, and we want this to be negative 1. This is 0.8, we want it to be negative 1.
Alright, so now we're going to do the mean squared error.
So how do we make the neural net now?
Okay, so now what I can do is I can do ypred.zip iter.zip y's, or actually wait, let's do it the other way around. y's.zip dot iter.zip ypred dot fold. How do we fold? The fold takes two arguments: an initial value, which should be 0, and a closure with an accumulator. So I think I should be able to do init, which should just be. Do we actually provide the init? I think so. And then we do y hat, and then it's going to be the square, right? And in fold folds with plus, right? No, it doesn't. Oh wait, so I need ac y hat. Oh, why? I gotta learn how to do these folds. And it should be, if it works how I expect it to, like ac plus y minus y hat dot pow f2. But this is not doing. Oh wait, actually, wait, but this is not right. Why is y hat? I don't understand what's happening here. Can I look at fold again? I don't get it. Why isn't that working?
Two things.
Yeah.
I'm ready to go. Are you?
So wait, I want to figure out this fold thing without relying on. So next, right? So wait, hold on. Wait, what if I do this? .2vec. Can I do this first? Okay, so now Y's is a vec of S64. Now we zip it. Dude, neural nets are so cool. I fucking love neural nets, bro. Neural nets are so fun. Neural network. There are 3 separate issues. Oops. Oh, but you know what it is, bro? Oh my gosh. Because we just need to do this. Because it actually is. This should work. Sub right hand side. What are the types? This is a vec of value. This is a value. So oh. Lel. What? Cannot subtract. I did that though. Impulse sub. Okay, I'm down to do this. So now we get a vec of. Yeah, because each of these are. Alright, it's kind of cringy, but whatever. I'm down to just unwrap the fold right now. Because that simplifies this. So now we have a value. But now I should be able to do y hat. And so this doesn't work, but that should be fixed by this. And why is this not working? No implementation for... Oh, do I need to dereference this thing? I have like a bug bite here. I think I need to dereference this thing. Yeah, there we go. Oh, that POW too. But we know how to differentiate through POW. Integer POW. Alright, so I think I did it. What? I don't get why this is not... Is it really because of this dereference thing? Oh, because this is a value? Dude, these value things are so annoying. No, that wasn't it. What? What is the error? Cannot add value to float. No implementation of float plus value. So what I need to do is take Oh wait, first off, this is confusing, right? This needs to be like that, and then we dereference. Oh, then we dereference this, or we reference this. That should be right. Expected float 64 found value. Okay, wait. Oh, but the accumulator... Oh, you know what? Oh, you know what? Actually, the accumulator... I think the accumulator needs to be... yeah, the accumulator needs to be a value. Cannot add value. Oh, I just need to dereference this. Or reference this. Okay, I think I figured it out. So the result of this thing, so let's print the loss. I think I did it. Or, yeah, sum of squared errors. SSE, not MSE. Right. Right, yeah, let's not do this. Okay, so we still haven't yet done any gradient descent, which is the next step. So now that we have... Oh, but why do these gradients look janky? Oh, because I know why. Now it's getting to be big. So 3.8. Dude, auto diff is so freaking cool, man. So now we need to do...
tune the weights to better predict the desired targets. And the trick used in deep learning to achieve this is to calculate a single number that somehow measures the total performance of your neural net. And we call this single number the loss. So the loss, first, is a single number that we're going to define that basically measures how well the neural net has performed. Right now, we have the intuitive sense that it's not performing very well because we're not very much close to this. So the loss will be high, and we'll want to minimize the loss. So in particular, in this case, what we're going to do is we're going to implement a mean squared error loss. So what this is doing is we're going to basically iterate for y ground truth.
Wait, he said mean squared error, but is he going to divide by the length?
So we're going to pair up the ground truths with the predictions, and this zip iterates over couples of them. And for each y ground truth and y output, we're going to subtract them. And square them. So let's first see what these losses are. These are individual loss components. And so basically for each one of the four, we are taking the prediction and the ground truth, we are subtracting them and squaring them. So because this one is so close to its target, 0.91 is almost 1, subtracting them gives a very small number. So here we would get like a negative 0.1, and then squaring it just makes sure that regardless of whether we are more negative or more positive, we always get a positive number. Instead of squaring the zero, we can also take, for example, the absolute value. We need to discard the sum. And so you see that the expression is arranged so that you only get 0 exactly when y out is equal to y ground truth. When those two are equal, so your prediction is exactly the target, you are going to get 0. And if your prediction is not the target, you are going to get some other number. So here, for example, we are way off, and so that's why the loss is quite high. And the more off we are, the greater the loss will be. So we don't want high loss, we want low loss. And so the final loss here will be just the sum of all of these.
Yeah, so okay, so he
So you
said
get
mean
zero,
squared error, but he
plus
actually
zero,
meant
plus
some squared error.
plus 7. So loss should be about 7 here. And now we want to minimize the loss. We want the loss to be low. Because if loss is low, then every one of the predictions is equal to its target. So the loss, the lowest it can be is 0, and the greater it is, the worse off the neural net is predicting. So now, of course, if we do loss backward, something magical happened when I hit enter. And the magical thing, of course, that happened is that we can look at n.layers.neuron, n.layers at, say, like the first layer, that neurons at 0. Because remember that MLP has the layers, which is a list, and each layer has neurons, which is a list, and that gives us an individual neuron, and then it's got some weights. And so we can, for example, look at the weights at 0.
It's called
It's not
W.
weights, it's called W. And that's a value, but now this value also has a graph because of the backward pass. And so we see that because this gradient here of this particular weight of this particular neuron, this particular layer is negative, we see that its influence on the loss is also negative. So slightly increasing this particular weight of this neuron of this layer would make the loss go down. And we actually have this information for every single one of our neurons and all their parameters. Actually, it's worth looking at also the draw dot loss, by the way. So previously we looked at the draw dot of a single neuron forward pass, and that was already a large expression. But what is this expression? We actually forwarded every one of those four examples, and then we have the loss on top of them with a mean squared error. And so this is a really massive graph. Because this graph that we built up now, oh my gosh, this graph that we built up now, which is kind of excessive. It's excessive because it has 4 forward passes of a neural net for every one of the examples, and then it has the loss on top, and it ends with the value of the loss, which was 7.2. And this loss will now backpropagate through all the 4 forward passes, all the way through just every single intermediate value of the neural net, all the way back to, of course, the parameters of the weights, which are the input. So these weight parameters here are inputs to this neural net, and these numbers here, these scalars, are inputs to the neural net. So if we went around here, we will probably find some of these examples, this 1.0, potentially maybe this 1.0, or some of the others, and you'll see that they all have gradients as well. The thing is, these gradients on the input data are not that useful to us, and that's because the input data seems to be not changeable.
I was thinking about that. It's like, actually, in some sense, I feel like there is probably some interesting stuff you could do about, well, I don't know, taking like an already very capable and general trained model and then looking at the gradients with respect to the input data. Like, maybe that's interesting. I don't know.
It's a given to the problem, and so it's a fixed input. We're not going to be changing it or messing with it, even though we do have gradients for it. But some of these gradients here will be for the neural network parameters, the W's and the B's, and those we, of course, we want to change. Okay, so now we're going to want some convenience codes to gather up all the parameters of the neural net so that we can operate on all of them simultaneously, and every one of them we will nudge a tiny amount based on the gradient information. So let's collect the parameters of the neural net all in one array. So let's create the parameters of self that just returns self.w, which is a list, concatenated with a list of...
Okay. Okay. So, one thing, so presumably...
self.d. So,
Okay, I have to go soon because I gotta go buy a bed. Okay. So, trait module function parameters self, and we want to flatten it, right? Okay, so now we have some work to do. Oh, you can actually... Oh, I didn't even realize that you could do that. That's pretty cool, actually. That's pretty cool. I didn't realize that you could do this. That you could actually define the function at the trait level, which makes sense, but that's very cool. Dude, Rust is such a great programming language. We're back. Okay, gotta hurry this up. Can I just do this? Can you splat? Okay. Alright, so we'll continue with that after I get a bed. But the thing is, when I clone... Yeah, I get it. Okay, cool. So that's it for right now. Solid hour of building neural networks. I'm actually having a lot of fun with this.